Hi everybody. How are you guys? To start here, I want to show you guys a little bit of something on the My Notre Dame. So if you go look at our My Notre Dame page, you'll see that I have the agenda for the rest of the semester kind of up here. So the goal here is to just finish chapter 5 and then we'll start the exam stuff. So that's what we'll be doing for the next 2 weeks, is just kind of finishing chapter 5. At some point in there, there'll be a homework quiz, but we'll worry about that when it gets closer. Everybody okay? So that's there. Yeah, what's up, buddy? Okay. All right. Before we move on to new stuff here, does anybody have questions from homeworks? I think at this point I asked you guys to work on worksheet 1 and 1 through 14, right? That sounds right to you guys? I think that's part of the problem set due on Sunday, right? We didn't make that due yet, did we? I don't think so. You might have done it already. I don't think I had it due yet.
Mr. Clue, can you just pick out a random one from 7 to 14 to do on the board?
Yeah. Does anyone have one in particular from 7 to 14 that they're particularly that one looks scary to me?
All of them? Yeah. Preferably like maybe 11.
11 sounds great. Let's do that one. Okay.
Yeah.
Oops, that wasn't. It was tangent, right? Yep. Okay. So the first thing that we like to do on these kinds of problems is look for any algebra things that we can do. Okay? Now, if I look, this thing is just a fraction, right? So the only thing I can do with just one fraction is to reduce, right? To be able to reduce this fraction, it's got to be in, like, the numerator and denominator would have to be in like factored form. Now the denominator is fine because it's just got one thing in it, but the numerator is an addition problem. Does that look like something you can factor? No, right? So there's nothing algebraic we can do here. So if there's nothing algebraic to do, now we're going to look for an identity that we could use. Now there's lots of identities here, but what Mr. Kulik sees is he sees like stuff that's squared, that's being added to each other. What type of identities have those attributes? The Pythagorean identities. So I'm going to go look at the Pythagorean identities and see if there's anything interesting that involves a sine squared, a tangent squared, or a cosine squared. Whoa! I see a great one. Sine squared plus cosine squared is 1. Where did I put my thing? What was I doing with that? Where's my stuff? Oh boy. There you go, Mr. Kulik. Let's put it where it's supposed to go. Come on, you stupid machine. Just do what I think it's what I want you to do. Just read my mind. Okay. So notice that we have a sine squared plus cosine squared. Did it matter that they weren't right next to each other? If I have three things that are being added together, does it matter what order I add those three things together? No, man. So it's cool. So I used P1 there. I'll just write that there so if you're going back and looking at the notes or whatever, you know what I did to do that. But sine squared plus cosine squared is 1. So I just took those two away and replaced them with a 1. Everybody good? Still doing okay? Sine squared plus cosine squared is equal to 1. So I replaced the sine squared and the cosine squared with a 1. So Alexis says, look at that numerator. That I recognized. We're just looking at the p's. Look at P3. 1 plus tangent squared. Well, that's the same as tangent squared plus 1, right? 2 plus 3 is the same as 3 plus 2. It doesn't matter the order I add things. Oh, wonderful. Wonderful. So use P3 there to replace this with just that. Now that fraction is written in a form I could reduce because everything is just multiplication, right? How would I reduce secant squared beta over secant beta? How to reduce x squared over x? How to reduce 4 over 2? That just turns into... Yeah, there you go. So we can just reduce a secant from top with a secant from bottom. And we're left with just secant beta. Did that help at all, Bella?
That sure did. Thank you.
Okay, you're welcome. Yeah, I don't either. Somebody make a choice. I'm forcing you guys to pick.
It's just the first one.
7?
Sure.
Okay. Okay, first thing we do is look for algebra things to do. Now, this problem is just two things multiplied together, correct? Are they like terms that I can combine via multiplication? Well, no. One of them is a cotangent, the other is a sine. Well, I can't do anything with that. Okay. So, it must be identity time. Notice that these are all to the first power, right? Cotangent times sine. None of them are squared or anything, correct? So the identities I will be restricted to are just going to be the reciprocals and quotients, because the other ones are squared or they're not just x's, right? So take a look at those and see if there's anything that looks useful. Specifically, I'd want to ideally be able to combine some like terms together. So I'd want to look for either a cotangent identity that is in terms of sine, or a sine identity that's in terms of cotangent. So if I look here, well, this is the only thing that I have for sine, but it's now in terms of cosecant. That's not helpful to me. Okay, what about cotangent? Well, here's cotangent, but that's in terms of tangent. That's not helpful to me. What else do I have? I have cotangent in terms of cosine over sine. That I like. Right? There's a way to turn cotangent into something with a sine in it. That looks good to me. Let's use that one. So all I did is I took cotangent and turned it into cosine over sine. Cool with that? So what I have now is two fractions multiplying to each other. How do I multiply two fractions together? This is like a late elementary or middle school question. We should be able to answer these sorts of things. Multiplying two fractions. What do you do? No! Cross multiplying is not a multiplication technique. That's a solving technique, you bozo. Just straight across, right? Now, what would be even easier than multiplying straight across? Right. Yeah, you reduce as you multiply, right? So these things that are on top can cancel with the thing that's on bottom. When I cross them out, what do they become? Just a 1, right? So now I have cosine times 1 over 1 times 1. Well, that's just cosine over 1, or cosine. Oh, okay. We're down to a single thing. That's as good as we can do. Who's next? You okay? Well, we can always come back and ask more questions later. That's no big deal. Today, we're going to start talking about section 5.3. In section 5.3, we're going to be doing, get ready for this. Everybody hanging on? Hold on tight. Proofs. It's okay. I promise it's okay. Because we're not doing like geometry proofs here. Okay? We're doing algebraic proofs. And that's a decidedly different thing. So this will have a little bit different feel to it. Okay, you're not going to be quoting theorems to do this. Okay? In all reality, it's the exact same thing that we were doing just a moment ago when we did those problems number 7 and 11 there. It's going to be the exact same process. It's going to be even easier, though, because it's essentially, we're going to have the answer already. Okay. So let's look at this. So I'm going to go through and do a bunch of examples and talk about a bunch of different strategies that we'll use to do these kinds of things. Okay. So our proof begins on one side and ends when we get to the other side. Do you think it matters which side you start with? No, it doesn't. It doesn't matter which side. Okay? In general, Mr. Kulik's advice is we want to start with the more complicated side. And your steps that you use to go from one side to the other that's your proof. Okay. So let's look at a couple of examples here that'll use some of these strategies, and then we'll list some more strategies and do some more examples and list some more strategies, do some more examples, and that's what this is going to look like today. Okay. So let's take a look at this example here. So we have two sides of our equation. We have like the left-hand side and the right-hand side. Which one of those looks more complicated? X squared minus 1 over x minus 1 minus x squared minus 1 over x plus 1, or 2? The left-hand side is definitely the more complicated side, right? Okay. So we're going to start with the left-hand side. So, same idea as when we did the simplifying problems just a moment ago. We can do two things. We can do algebra things, or we can use identities. Now, is there even any trigonometry in here? So are we going to be even using an identity as an option here? No. It's all going to be algebra things. Everybody's cool with that? Okay, so when we talk about algebra things, what do we mean? We mean like factoring, or foiling, or combining like terms, or making common denominators, or reducing fractions. Things like that. Everybody's cool? So if I look, what do I have right here? What is this problem really? I'm subtracting two fractions. Everybody agree with that? You look at this. Yeah, it's complicated looking, but it boils down to just subtracting two fractions. Yeah? So, what are the things I can do with fractions? I can reduce. So maybe these fractions can reduce. Or I might be able to make, or I might need to make a common denominator so I can subtract them. Which one should I check first? Reducing, right? That's going to be easier than making a common denominator to subtract these things. So let's check to see if I can reduce first. Okay? Bless you. You're welcome. How do I reduce a fraction? Just as like a review, you know, like what if I have 4/6? What's that reduced to? Okay, it goes down to 2/3. How did you get 2/3? You did like a prime factorization, and then you could reduce a factor in common from the numerator and denominator, right? Everybody agree with that? It's like how we reduce a fraction. Everybody agree? So in order to reduce, what did we have to do? We factored, right? Okay. So let's look at this fraction. How do I factor x squared minus 1? This is the one thing you guys told me you practiced so much of last year in your Algebra 2 class. That you did factoring forever. How do I factor x squared minus 1? Well, that's a difference of 2 squares, right? X squared is just x squared, and 1 is just 1 squared. So how does x minus 1 factor?
X minus 1,
Great. Okay. Can I factor x minus 1? Right? It's a degree 1 polynomial with no greatest common factor, so no. Right? There's nothing I can do with that. And similarly, there's nothing I can do with x plus 1, right? It's a degree 1 polynomial with no greatest common factor. We call those things monic. It's the same thing as prime. Okay, so I have that. Can I reduce? Great, you said yes. What can I reduce from the first fraction? The whole top?
No, minus 1.
The x minus 1s can cancel, right? In the second fraction, what can cancel? X plus 1s. So what am I left with? X plus 1 minus x minus 1, right? Does that look good to you guys? Everybody agree with that? You're all wrong! You should have disagreed with me. I made a mistake. I made a mistake on purpose to illustrate to you how easy of a mistake this is to make. Does anybody see where the mistake is?
No. Oh, the parentheses?
Yeah, parentheses where?
Around x plus 1 and then x minus 1.
Well, I really only need it around the x minus 1. Why do I need it there but not at the front of the x plus 1?
Separated from the minus.
That negative sign needs to distribute. Is there a negative sign in front of the x plus 1? No. There's nothing to distribute. I don't really need to have the parenthesis there. If you put them there, it's not incorrect. Okay. What can I do now? Great! So x minus x, what's that? 0, okay? And then 1 plus 1 is 2. I'll just cross those out. And what were we supposed to get? 2. So we're done. That was our proof. We did it. Where's the proof? That work was the proof. Did I make 2 columns? Did I use any theorems? No. You know why? It's an algebraic proof, not a geometric proof. Calm down. It's okay. Is this really different than what we were just doing? No, it's the exact same thing. It's just, in fact, it's even easier because I know what the answer I'm supposed to get at the end is. Oh, well, we can do this. This isn't quite as scary as when you said the P word and I almost soiled myself. I mean, it's scary, people. It's not scary. Okay. So let's talk about some more strategies to kind of refine what we've been doing and do another example. And this one will involve some trigonometry also. Okay. We're going to consider addition and subtraction to be more complicated than multiplication division. So when we talk about which side is more complicated, if I have 2 things added together versus 2 things multiplied together, the added side would be the more complicated side. So in general, we want to look for algebraic things to do first before looking for identities. So again, algebraic things: factor, FOIL, combining like terms, reduce, common denominators, things like that. And then my last strategy here for right now, if we're unsure of the identity, convert everything to sine and cosine. Okay. Example time. We got a left-hand side, we got a right-hand side of our equal sign. Which one is the more complicated side? The left side, because addition versus multiplication. Okay, good. Okay. So we're starting on the left-hand side. First thing we want to do is look for an algebra thing to do, right? Here we have 2 things added together. When can I add 2 things together? Only if they're like terms, right? Are these like terms? No. Could I factor this? No. They're not squared, and there's nothing in common between them. So nothing algebraic to do. You guys agree with me? Does it help when I'm talking through exactly like why I'm making the decisions I'm making and like what I'm looking for? I'm trying to be really careful about it. So, on to identities. Are you sure what identity to use? What should you do if you're unsure? Yeah, I want to try to get everything written in terms of sine and cosine. So I'll go to my identity sheet, and I'll look at my identities for tangent x and cotangent x. Since those are just, they're not squareds, and it's just an x in there, the only identities I should be looking at are the reciprocal and quotient identities. Okay, tangent, 1 over cotangent, that doesn't have sine and cosine in it, I don't want to use that. Cotangent, 1 over tangent, that doesn't have sine or cosine in it, I don't want to use that. Tangent is sine over cosine, I'll use that. And then cotangent is cosine over sine, I'll use that one also. So I'll use Q1 and Q2. Okay. What do I have here? Two fractions being added together, right? Everybody agree? If I have two fractions being added together, two things I can check. See if they reduce. Can I reduce either of these? No. The reason I can't is they're not factorable. And there's no like term between the numerator and denominator, right? Okay. So I can't reduce the fraction. If I want to add them, then what do I have to have? Great, a common denominator. What would the common denominator be for sine x over cosine x plus cosine x over sine x? Well, if I had 2/3 plus 1/2, what would the common denominator be there? 6. How'd you get 6?
So for this would be cosine x times sin x.
So you multiplied 2 times 3 because 2 and 3 were relatively prime, right? That's how she got 6. Now, is there anything in common between cosine x and sine x? No. They're relatively prime. So the common denominator is just going to be cosine x times sine x, exactly as you said. I just wanted to like fill in the steps there about how you got there, because you got there quicker than I expected. But that's great. So what do I need to multiply the first fraction by for the denominator to turn into cosine x times sine x? Well, just sine x over sine x. What do I need to multiply cosine x over sine x so that its denominator is sine x times cosine x? Cosine x over cosine x. That's right. If you know it, just shout them out. That's what I'm looking for. So what we did there is we just made a common denominator, right? Okay, what's sine x times sine x? Well, what's x times x?
Oh, sin x.
It would be x squared, right? So this is going to be sine squared x. And what's cosine x times cosine x? Cosine squared x. Very good. And that's going to be all over sine x times cosine x. Everybody cool so far? What do I have here? Okay, first thing I'd want to say, yes, but let's put a hold on that. I have a single fraction. What can I algebraically do with a single fraction? Reducing would be the only thing I can do. Can I reduce this as it's currently written? No, because the numerator isn't written in factored form. There's addition going on. So could I factor sine squared plus cosine squared? No, right? Remember, although there is a difference of 2 squares, there is no sum of 2 squares factoring pattern. A squared plus b squared just is not factorable. Okay, so there's no possibility for me to be reducing this because I can't factor that numerator. So what do? There's nothing algebraic to do. Look for an identity. Okay. What stands out to you guys? Everything's already in terms of sine and cosine, so that option has flown the coop. Hopefully this stands out to you because I have things squared that are being added. What kind of identities do I go to look at then? The Pythagorean. So I go and I look and say, aha! P1. Sine squared plus cosine squared. That's what I have. That's just equal to 1. Fantastic. Everybody's okay with that? All right, let's pause here and take a look at where we're trying to get to again. We're trying to get to that right-hand side, which is just 2 things multiplied together, correct? So what I want to do here next is I'm going to rewrite this fraction as the product of 2 fractions. Right? Remember when I multiply 2 fractions, I just multiply the tops together and the bottoms together. So the way I've written this is still the same thing as what I had, right? What do I call this? Maybe this is just like rearrange or something. That's some terrible penmanship, Mr. Kulik. It's hard to write on an angle, guys. That's not any better. I'm quit. Life is hard, guys. Okay. Well, I have 2 fractions multiplied together. I mean, if I try to do an algebra thing, the only thing I do is multiply the 2 fractions. I'm back to what I just had. So that feels like a dumb decision to me, right? So identity time, I guess. So I'm going to look for 1 over sine. Well, that I know I'm going to have to be in the reciprocal identity land. Let's see. 1 over sine is cosecant. Great. What else did I have there? I had 1 over cosine, which is secant. Okay. Well, I'll just use R4 and R5 then. That seems like a good decision. Oh my goodness, Mr. Kulik. Where am I at now? Where was I supposed to get to? That! Oh, that must be done then. I'm trying really hard to be excited about this, guys. I know it's scary for you. So, because I used that terrible P word to start the class. And everyone was just like, oh no. So I'm trying hard to make this like less scary than it sounded. How am I doing? Is anybody terrified? Not anymore. It was scary there for a minute though, right?
Yeah.
Is it getting easier? Just feeling better? We'll keep going. I have another whole page of examples and stuff. Okay. My next two strategies. This difference of two squares factoring pattern often will be our link to the Pythagorean identities. And vice versa, I should say. Using the Pythagorean identity may unlock a difference of two squares factoring thing we can do. So those two often get paired together. That's nice to kind of have. And then the second piece is this observation that we made last time, that keeping in mind where you're trying to get to, keep your eye on that target, where am I supposed to end up at, can often give me some insight as to what to do. Oops. Right, if I go look at that last problem, this step was probably the trickiest one to think to do. How did I make that observation? Well, I went back and looked at where I was trying to get to and saw that, oh, it's supposed to be two things multiplied together. How can I write this one fraction as two things being multiplied together? So we're just going to kind of use that. All right. Which side is the more complicated side on my example here? Do I have to call on people, or are you going to volunteer? I'll do it, guys. I'm not scared. Left side, I agree. Why? It's addition. Excellent. Thank you. Was that so painful? I mean, maybe it was. I don't know. If it is, like, suck it up, Buttercup. Okay. What do we got here? Two fractions being added together. What are the two algebraic options I have? Reducing, and then like making a common denominator. Can these reduce? No, why not? You got a 1 in the numerator, right? Immediately I know that those can't reduce because 1 over something, it's like a unit fraction. They're not reducible, right? Okay, so we need to make a common denominator and do the adding. Great. What's the common denominator going to be between 1 over secant x minus 1 and 1 over secant x plus 1? What would the common denominator be? Well, when I added 1/2 and 2/3, what would I do then? Or what was my common denominator then? One half and 2/3. What was my common denominator when I added those? 6. How did I get 6? 2 times 3, because 2 and 3 were relatively prime. They didn't have any factor in common to each other, right? How about secant x minus 1 and secant x plus 1? Are those have anything in common between each other? No. No, they don't. So what's the common denominator going to be? Secant x plus 1 times secant x minus 1. Okay with that? What do I need to multiply the first fraction by to get that common denominator? There you go. Thank you. Excellent. And what do I need to multiply the second fraction by? Excellent. Let's go ahead and add some parentheses in here so we don't forget that what we're really going to be doing here is like foiling and distributing and stuff, right? So we made our common denominator. So distribute in, well, that's just going to give me secant x plus 1. And then I have my plus sign. And then I'll distribute here. And my common denominator is on the bottom. Everybody cool? Any algebraic things you notice that you could do here? Look at the numerator. You can combine some like terms, right? What's secant x plus secant x? Those are like terms. What's x plus x? So what's secant x plus secant x? 2 secant x. There you go. Do you like how I keep bringing it back to the same rules you already know?
Yeah.
I'm trying very hard to just connect it to stuff you're already good at. Matt? Absolutely. And then I have 1 and negative 1. Those just cancel out, right? Everybody's cool? Look at the denominator. What could you do with that? No, they're not being added. They're being multiplied. That's a FOIL problem, isn't it? Now, when I FOIL that out, notice that this is like a plus b times a minus b, right? So, do I really need to go through all the trouble of FOILing? Nah. I know it's just going to be a squared minus b squared. So secant squared is just secant squared, and 1 squared is just 1. So. Are we okay? Doing all right? All right, we're down to a single fraction now. Can I reduce this fraction? What do you think? Can I cross out the secants? Think hard about this. This is a very important question I'm asking right now. We're down to a single fraction. Right here. Can I go and do that? Bella, you said no. That's the correct answer. Here's the important question, though. Why not?
Because top and secant squared.
Well, I'm just canceling out the squared sign on the bottom, not the whole thing.
Oh. Then I don't know.
The answer is still no. Ryan, what's the problem? It's not the 2 that's the issue. It's the -1. The denominator is not in a factored form. You can't reduce unless things are in a factored form, right? It has to be all multiplication. The denominator is 2 things not being multiplied, they're being subtracted. So I cannot reduce like that. Everybody's okay? Again, my analogy to you guys would be like, if I had this, what's the answer to that? That's 4, right? I definitely can't do that because I would get -2. Right? Mm-hmm. You guys see what I'm saying as to why I can't reduce that way? It's clear when I put numbers in there. If you're ever uncertain, like, can I reduce like that? Just rewrite it with numbers in the place and see if, you get the same answer both ways. That's a nice trick to tell you if, like, yeah, can I do it that way? Okay, so I can't reduce that. What should I do then? Identities. What did we just have here? That was a difference of 2 squares, correct? What set of identities often pair well with the difference of 2 squares? Pythagoreans, right? That was one of the things in the strategy I just hinted at. So I'm going to be looking here, secant squared -1, and the Pythagoreans. Oh boy. P3 looks nice because I can replace that secant squared with tangent squared +1. What do you notice now? Look for algebraic. Look at the denominator. Yeah, the +1 and -1. Pfft. Well, that's nice. Uh-oh. I locked the door. Can somebody open that for her? Come back at some point. All right. I'm down to a single fraction again. This time it's in a form that I could reduce because everything is just being multiplied. Is there any reducing to do, though? No, right? There's not a common factor to the numerator and denominator. What should I do then, Mr. Kulik? Mr. Kulik's advice is eye on the prize. Okay, where are we trying to get to? We want 3 things being multiplied together. So I'm going to rearrange this just so I have 3 things multiplied together. So I have 2 times secant x times 1 over tangent squared x. Right? The numerator multiplied together times 1 over the denominator. Everybody cool with that? See why we did that? You see how looking at where I was trying to get to informed me to do that? This is probably the hardest thing, this little piece here, being able to look at where you're trying to get to and do a rearranging thing like I just did there, is usually the hardest thing for kids to get good at. That's why I'm pausing here and really letting you soak it in. Everybody's cool with how I took that fraction and broke it apart into the product of three things? While doing that, I love that I see the 2 there. I don't have to mess with that anymore. That's all set. Now somehow secant x and 1 over tangent squared have to turn into this, right? Well, I see something here. I remember that tangent and cotangent are reciprocals because I notice here that I don't have any fraction. So let's get rid of this fraction, right? So use the reciprocal identity to do that. So I have 1 over tan squared. If I go and I look here, 1 over tangent is cotangent. So what's 1 over tangent squared? Excellent, thank you. Oops, I think that was R3, right? Let's go back and double check. Nope, R6. Now, are you guys required to put like this stuff on the equal signs like I'm doing when you're doing your proof? No, man, it's fine not to do that. I'm just doing it so that like if you go back and look at this, you have some clue as to what just happened here? How did he do that? You know what I mean, guys? All right. Well, that gets us a little bit closer, right? The problem here is, though, that I have a cotangent in my answer, but a cotangent squared in my problem. Well, that's not that big of a problem, though, because what is cotangent squared the same as? Well, let's backtrack a second. Can I rewrite cotangent squared as a multiplication problem? What's x squared the same as? That's right, Alexis. Cotangent x times cotangent x. So there's the first 2 parts of my answer now, right? And I know somehow that cosecant has to become cotangent over secant, or cotangent times secant. It has to turn into cosecant, right? Okay, well, let's go look for an identity that relates those 3 things together, cotangent, secant, and cosecant. Cotangent is cosecant over secant. That involves all 3 things right there. Now, would you find these this quickly when I'm finding these? Probably not. You'll have to look for a minute. I'll give you a little hint here, though, guys. And I know this kind of stinks. If you have these identities memorized, it goes so much faster and it's so much easier to get good at these. I know. But all I'm really talking about is like the reciprocal, the quotients, and the Pythagoreans. You don't need all of them. But if you had those 3 sets memorized, Whoa! This gets so much easier. Okay, where were we? What can I do with this? What can I do with this? It's an algebra thing. If I have 3 over 2 times 2, what does that equal? Shouldn't have to think about it.
12.
No, man, just 3. 2 is 2 over 1, right? That's okay. Just 3. Why did I ask this question? Isn't that the same thing that we have here? And now what happened? We got exactly what we needed. I know that was a long one, guys. Mr. Kulik, are they all going to be that long? No, you've seen a bunch that weren't that long. That one was just a toughie because there wasn't a great, efficient, short way to get there. Let's do another one. What do we start? Got to pick the more complicated side. Which side is the more complicated side? Oh boy. There's a right answer to this, but it doesn't really matter for this problem. The right-hand side is more complicated because that's one I can rewrite as this, where I have a common denominator. So this one is technically an addition problem. I can't do the same thing here because if I write cosine over 1 minus cosine over sine, that doesn't have a common denominator. It doesn't go back together. So this one is an addition problem. This is just the left-hand side is a division problem. That's fine. I mean, it doesn't, for this problem, it would not matter. It doesn't make it any more complicated to do pick the other one. But technically speaking, the right-hand side is the one you want to use. But it doesn't matter in this problem. And that would often be the case. So let's just say for the sake of argument that we did choose the right-hand side. Okay, so start with algebra things. We have one fraction. Can we reduce this? What do you guys think? Reducing I can do for 1 plus sine t over cosine t? Somebody take a risk.
Yes.
How would you do that?
Multiply 1 minus
Oh, I see. So, okay, so you're not talking about reducing then. You're talking about doing something else, which is great. That is a good idea. I like that idea a lot, but there's no reducing I can do here. There's not like something I can cancel like that. But your idea of multiplying the top and bottom by 1 minus sine t is excellent. Why in the world did you come up with that idea?
So you can get the top to be 1, and then we can...
Well, I think the top won't become 1, but here's the key, is look at where you have to go. You have to have a 1 minus sine t at the bottom. How the heck am I going to turn cosine t into 1 minus sine t? I don't know. Let's just multiply and put the 1 minus sine t in there, right? Why is it okay to do this? Why can't I just multiply the top and bottom of this by 1 minus sine t? Why is it okay to do that? This is the right idea. I'm super excited that you had this idea. It's a great one. But why is it okay to do that? Because it's both the top and bottom are the same, meaning all you're multiplying by is 1, right? And I can multiply by 1. That doesn't change anything. Okay. And I'm going to go ahead and FOIL at the same time here. Jeez. Yeah, that was a big one, guys. Sorry. Okay. Notice in the numerator, I have a difference of 2 squares, right? So I'm not going to write out the FOILing. I'm just going to use that factoring pattern to write that as 1 minus sine squared t. What did we just have here? That was a difference of 2 squares, right? What identity is almost always going to be followed? Pythagorean. So let's go and look at our Pythagorean identities. I see it. I'm going to use P1. What? How are you going to do that? Well, I'm going to replace this 1 with sine squared plus cosine squared. And then I still have that minus sine squared. And we're all over that stuff. Well, what good did that do, Mr. Kulik? Look at the numerator, guys. What can I do up there? Yeah, I have a sine squared and a minus sine squared. Well, those just cancel each other out. That's exactly right. Excellent job. Okay. Well, I'm down to a single fraction now, right? And if I look, this is in a form where I can reduce, right? I have just something squared on top divided by 2 things multiplied together. Does everybody see that? How can I reduce that? I can cancel a cosine from the top and 1 from the bottom. That leaves 1 cosine still left on top. And wait a minute. Wait a minute, by George. Isn't that what we were looking for? Rock and roll. Again, eye on the prize. Super helpful to me because coming up with this step would have been tough to just decide to do that for no good reason. Right? Looking at the answer that you're supposed to get and go, I don't know how the heck cosine is going to turn to 1 minus sine. But the top gives me a difference of 2 squares. If I do that, that feels pretty right. Feels pretty right. Those are good ideas. All right. Final strategy and final example. Okay. Final strategy. If you're stuck, you can work on both sides and meet in the middle. So if I take a look at this, next one, which side is the more complicated side, left-hand side or right-hand side? They're tied, right? The left-hand side is the division of two things. The right-hand side is the product of two things. Multiplication and division are equally complicated. It's really a tie for first. Okay, so it probably doesn't matter which side we start on. Well, and it's not, because if you guessed, we're going to work on both of the sides a little bit and meet in the middle. So let's just say we start with the right-hand side. Or, the left-hand side first. Okay, single fraction. Can I reduce this? No. Not as it's currently written. Okay. Well, I guess it's identity time. Like the only thing I can really do with a single fraction is to try to reduce, and I can't do that. What identities do you think what identity do you think I would want to look at? I'm going to look at it for a Pythagorean. So I have cotangent squared. If I subtract 1 from both sides, cotangent squared is the same as cosecant squared minus 1, right? Everybody okay with that? Now, I don't do that very often, but like in this case, it's kind of what I need to do. Why am I stuck on this one? Why don't I do something different? You'll see in a second. Where did my stick go? There it is. And I'll call this like P2 star, right? I used kind of like that altered version of P2 that I just showed you. So, got still a single fraction. The only thing I can do with a single fraction is to reduce. To reduce this, is this in a reducible form? No. What would I need to do to get it in a reducible form? Because I see things that are the same in the top and the bottom, right? They both have cosecants. They both have 1s. Feels like there's going to be some kind of reducing that can happen. Well, what am I going to have to do first to be able to get this in a form where I can reduce it? Starts with an F. Factor. What part can factor? The top or the bottom? The bottom is a degree 1, right? There's nothing squared down there. So the bottom is not going to factor. The top. Yes. Hopefully you recognize that the top is a difference of 2 squares. Eek. That was a bad looking U. Oh, am I out of time here, guys? Yeep. All right. For next time, what I'd like for you guys to work on is '47 to 52. 47 to 52. Next time, listen for me, please. Next time, I'm going to call on 6 random students to write their answers on the board. And we're going to talk about what they did that was good or bad or could be improved or mistakes. I'm warning you that we're doing this so that you can have some semblance of work done and you're not like, I didn't do anything. Okay?
I'm going to be one of the 6. I already
Please do your own work. It's okay to make mistakes. I don't expect anyone to have a correct answer.
God, I hope I don't.
Okay? And you know what? I hope we all look kind of stupid because you know what it does? It's opportunities to learn. You get to see what mistakes are, why you're making mistakes.
47 to 52.
Correct.
All right. I'll be ready.
Good.